Good morning one and all. So let us start today's class. So in the last example we are dealing with a sigmoid neuron. In sigmoid means a family of functions. In sigmoid specifically we are dealing with a logistic function. Okay. Now, so what is the sigmoid? Everything I told you in the last class. Now this is a sigmoid equation. Okay. So actually we have a x, that is set of inputs x1 so on xn, and for each and every x we have a output y, isn't it? It can be binary or real, or belongs to a real line. Now, so always there is a true relation between y and x. There is a true relation between these two, x and y, but we don't know that. So what we do is we are approximating the relation between x and y with the logistic function. Okay. In our case, what is the logistic function? Y cap. This is approximation or the prediction. 1 by 1 plus e power minus w transpose into x. Okay. So now we are approximating the output with this function, but with the true function output is y. This is a real output or true output. This is a approximation or prediction. So if both are happen to be same or approximately equal to same, then our prediction is perfect. Okay. Now obviously, so there will be errors, right? So that can be dealt with what? Loss function or error function or objective function. So loss, it depends upon w and b. I will tell you what is b. Okay, so for time being we are writing only w, no problem. So what is that? It is the square error, I equal to 1 to n. So yi minus yi cap whole square. Yi minus yi cap whole square. So what is yi? That is a actual output. What is this yi cap? That is a predicted or approximate output. So actually what is yi? What is yi cap? It depends upon 1 by 1 plus e power minus w transpose into x. Okay. So for specific w and x we get yi cap. So yi is the actual output. Anyway, now let us proceed further. Now our aim is to minimize the loss. Okay. Actually we should make loss or error to be equal to 0, but that is very hard. Okay. So what we do is we try to minimize the loss function. Okay. So we build a network such that the loss is minimized. Okay. Yeah. So why you are taking the square of the errors? Because as I told you just now, error can be sometimes 0.5, sometimes minus 0.5. So if you add without squaring them, obviously the result is 0. It gives a false impression that there are no errors, but actually there are two errors of equal magnitude but the different sign. Okay. So to avoid such confusions, we take the square of the errors, sum of squares of the errors. Okay. Next. Now, so here we have to learn the parameters here. So here w and b are the two parameters which has to be learned from the data. Why? Because if you learn these properly, if you know these values properly, your approximation will be good. That will be approximately equal to the actual values. Okay. So everything depends upon the values of w and b. So we have to learn these values properly from the given data. Okay. Now, so as I told you, so we are writing the most sophisticated form of sigmoid function f of x for specific x 1 by 1 plus e power minus w transpose x plus b. Okay, now here this is the learning the parameters from the guesswork. Okay, as I told you just now, we need to learn the parameters. What are they? W and b. So how to learn them? So let us go by the guesswork, guessing. You have to guess them. So but guessing is a impractical thing actually. Okay, let us see why it is impractical. Okay, so to make the lives easier, I am assuming only one input. Only one input. Okay, so obviously y cap is the output of the sigmoid function, that is a approximate or the predicted value. Okay, so what is f of x? I wrote it just now, right? This is f of x, this sigmoid function for y cap. Here, otherwise, to avoid confusion, let me write like this. So y cap equal to sigma of x, that equal to 1 by 1 plus e power minus w transpose into x plus b. Okay. Now, so one output, and not only that, so sigma stands for sigmoid function, logistic function in this case. Okay. For ease of explanation, we consider a very simple version of the model. We having one input. So further to be consistent with the literature, from our one, we will refer omega naught as b, that is bias. Okay. Actually, omega naught is a bias, but we call this as b. Why? Because b stands for bias. The first letter of bias is b. So that's why from now onwards, I will refer bias as b, not omega naught. Okay. Now this is 1, this is bias, this is input, this is the weight of the input x. Now this is the sigmoid function. Okay. So for simplicity, I am taking only one input. So now actually, so what you have done? So actually here the job of this neuron is to guess or to find out whether I like a movie or not, dislike or like. Okay. So instead of that, I am giving input x as the critics rating, which is a real number. Okay. Critics rating is a input to this setup or network. Okay. So instead of this like or dislike, I want to predict the IMDb rating, which is also a real number. Okay. So input is a critics rating CR, output is the IMDb rating. So from this network, I want to guess, I want to find out the IMDb rating by taking critics rating as input. Okay. So there is no reason as such, but I just want to find out the IMDb rating and critics rating. So I want to know the relation between IMDb rating versus critics rating. Is there any relation or not? Okay. So that is our job. So we build this network to find out the relation between IMDb rating and the critics rating. Both are happen to be a real numbers. Now I am taking only one input, that is x, that is critics rating, and bias is called as b. Okay, that's it. Okay. So for here now, so what is the sigma x now? What is the function now? Since there is only one input and one w. Okay. So w transpose x, everything was there now. So w is nothing but w only. One value is there. X means x only. Only one value, one input, one weight. Now everything becomes 1 by 1 plus e power minus wx plus b. Is it okay? There is no transposition is required because now w is not a matrix, it is simply a value. Why? Because I am taking the simplified version of the sigma neuron having only one input. Obviously, to this input, w is the associated weight, and instead of omega naught, w naught, I am calling that is as bias b. Okay. Now this is the sigmoid function for the above example. Is it okay? Right. Okay. Right. So here first of all we have to train the network. So we have to give the data. So we are giving n pairs of data. What is that? Suppose for each and every movie, so we give xi and yi. What do we give? What we give is we are giving a pair of data points x and y, xi, yi. Okay, what is xi? What is yi? So suppose this is xi, this is yi. Okay, so for each and every movie we give the what is xi? This is a critics rating, CR. What is this? IMDb rating. I am giving the values. So A1. So let me take otherwise R1, B. Sorry, A. Let me take A here. A1. So on, so on. Okay. So for n movies, I am giving the data. What is data? What is the critics rating and what is the IMDb rating? For how many movies? N movies. So I get a pair of n values like R, R1, A, A1, so on, so on, up to n pairs. Okay. So this is the data for the network. For this is training data for the network, sigmoid neuron. Now, so here in this function, what are the parameters to be learned from the data? W and beta, W and B. Okay. So we have to learn these parameters W and B such that the last function will be minimized, such that the last function is minimized. Is it okay? So everything depends upon how perfectly you are learning these parameters W and B. If you learn them properly, the loss function will be very, very less. Otherwise, the loss will be more or error will be more. Okay. Now, so what does it mean to train the network? So first of all, we are training the network by giving the data of n movies. Okay, n pairs of data. They contain a critics rating and the IMDb rating. Okay, we have to train the network first. Okay, suppose we train the network with two values, 0.5, 0.2, 2.5, 0.9, which means suppose we are training the data, we are training the network with suppose what are the points? With the only two data points. Okay, what are they? This is a critics rating, this is the IM. What are you training with? 0.5, 0.2, 0.5, 0.2. This is a one data, one pair. Other pair is 2.5 and 9, something like this. 2.5 and 0.9, right? Okay. This is the training data. Assume that I am giving only 2 points. Now, at the end of the training, we expect to find W star, B star such that, what should happen? So after training, so we have to learn the weights. For example, let us take W star, B star. We have to learn these weights from where? From the given data. So that when you substitute f of otherwise in the sigmoid function, if substitute 0.5 in the sigmoid function, it should lead to what? Approximately 0.2. If I substitute 2.5 in the sigmoid function, it should approximately equal to 0.9. Are you getting what I am saying? Is it okay? So then the sigmoid function is correctly identifying the outputs. Is it okay? So if substitute 0.5, it should be leading to 0.2. If substitute 2.5, it should be leading to 0.9. Is it okay? What are these two? Actually, these are the true outputs, actual outputs. These are the inputs. Where are we substituting? In the sigmoid function. What is the function? Here. Okay, in the function, what are the unknown parameters? WB. So if you learn these parameters properly from the data, training data, obviously the sigmoid function will be converges to the true values or actual outputs. Okay. Then the network works perfectly, right? Next. In other words, so we hope to find a sigmoid function such that these 2 points lie on the sigmoid function. Yeah. So what do we do? So if you draw the sigmoid function, okay, if you draw the sigmoid function, so these 2 points should lie on the sigmoid function. These 2 points should lie on the sigmoid function. Then there is no problem. Loss will be approximately 0. Is it okay? So we should learn the weights. The important task is learning the weights from the data, training data. We have to learn the weights, parameters, that is W and B, such that all the data points lie on the sigmoid function. If they don't lie, obviously there is a loss or error. Okay. So can we try to find such W star B star manually? Okay. So let us try manually. Okay. So manually, so randomly I am guessing W equal to 0.5, B equal to 0. So randomly I am assuming, randomly I am guessing. There is no specific reason why I am guessing like so. It is random in nature. I am saying W equal to 0.5, beta equal to B equal to 0. Now what is sigmoid function? Now sigma x equal to 1 by 1 plus e power. Actually it is minus wx plus b, isn't it? B is 0, w is 0.5. Now it is simply becomes 1 by 1 plus e power minus x by 2. Is it okay all of you? This is my sigmoid function for the given w and b. So I am taking initial random guess. I am taking these values initially because I am going for guesswork. Okay, I am just guessing. Okay, now, so now if you do so, now where is the sigmoid function? Now if you draw this function 1 by 1 plus e power minus x by 2, it is something like this. Okay, obviously these 2 points are not lying on the sigmoid function. Is it okay? Obviously this is a bad guess. How bad it is? It depends upon the loss that you are getting from these 2 values. Okay, initially, so if this is the proper sigmoid function, all the data points are lying on the sigmoid function. All means here in this case only 2 points. In this case loss is 0. But if you take W equal to 0.5, B equal to 0, what I am getting? I am getting a bad approximation because the data points are not lying on the sigmoid function. So obviously there is a loss. How much is the loss? That is given by the loss function. Okay, this is a loss function. Okay, so here actually this is a loss function. Okay, let me write here. So the loss function is 1 by 2 into, actually we have only 2 data points. So I can say the actual output minus f or sigma, no problem, you can write sigma x1 whole square. This is the loss for error square plus y2 minus sigma x2 square. Actually, so there is no 1 by 2 initially, right? But so whether you write any value here, it doesn't make any difference. Is it okay? So actually in the formula, there is no 1 by 2. Initially I told you the formula of loss function. Is it okay? WRB, okay. So now this is loss function. Now this is loss function What do we write? Loss of because of two parameters W and B. Now actually this 1 by 2 is not there initially. Let me go back. Somewhere here I mentioned here. So 1 by 2 is not there actually. So you can write any positive quantity here, any k which is positive. So it doesn't make any difference. But why I am writing 1 by 2? Because so generally to find out the minimum loss, what we do to find out the minimum or maximum of any function, we do differentiation. So if you do differentiation, so what will happen here? 2 comes here, 1 by 2, they will cancel out, right? So for that convenience, we are writing 1 by 2. So you can write any number here which is always positive, any k which is positive. It doesn't make any difference. Okay, because loss depends upon x, w and b. Okay, so you can write any number here, no problem. But in this case, let us go with 1 by 2. The basic reason is if differentiate 2 comes here, no, 1 by 2 cancels out. So that becomes very easy to calculate. That's it. Okay, anyway. Now you can substitute all the values. What is x1 initially? X1 is 0.5 and so substitute 0.5. So you get the sigmoid values. Actual value is 0.2. 2.5, f of 2.5 means the output of the sigmoid function. 0.9 is the true output. You find out, you get 0.073. This is a loss which is not close to 0. How much loss you are getting? 0.073, which means so the amount of loss you are getting for W equal to 0.5 and B equal to 0 is how much? 0.073. So this is the amount of loss you are getting, something like that. Okay, or error which is not close to 0, but we try to minimize the loss, that is WP, loss function or error function or objective function. All mean same, all are all right. So let us take few more guesses. See, initially I have taken this as a guess. There is no specific rule why I am taking these values. Initial guess, that's it. Okay. Now, so let me take some other guesses. Okay. Now I am taking minus 0.100. What happened? I got loss which is more than the first row. In the second row, the loss is more than the first row. Now we can make an educated guess now. Why? Because we got two rows. First row the error is 0.07. In the second row the error is 0.14. Error is increased. Why it increased? Because I have made W is negative, which means W should be positive. Why? Because in the second row, when you make W as negative, the error is the loss is increased. So let us take W positive and B negative. In the third row, 0.94 minus 0.94. The error is 0.0214. It is less than the first case in the first row, which means so we can make an educated guess, not random guess. We have some education. Okay. Now what we do is we increase W and decrease B. Okay, you do like this. Increasing W, decreasing B, or increasing W positively, decreasing B negatively. Okay, if you do so, some point of time you are getting almost zero errors or zero loss. Okay, it is everything about guess. Okay, there is no specific rule for this. Okay, now so what happened here? Finally, this is what we are getting. So initially we started with this sigmoid function. Next, red color. So this is the next guess. So and so on. I have shown everything here. Is it okay? Now, so finally, for these values, it is exactly something like this, somewhere here. Okay. So we are making educated guess based upon the data. See, we have made a guess based upon what? These values. Is it okay? We have some intelligence over this, isn't it? Right? Now anyway, this is not the proper way of doing this. This is not a proper way of learning the weights. Okay, so we have better than this, that is called error surfaces. Okay, something better than the guessing work or guessing algorithm. Something better than the guessing algorithm. Guessing is not good way anyway. So in the guessing we have taken few values of W and B. Okay, but so instead of taking few values, let us take all the values of W and B in a certain range. Okay, so we can do so because we have 2 points and 2 parameters. What are 2 points? Xi, yi. 2 parameters W and B. We can easily plot these values for different values of parameters. Okay, that is nothing but error surface, which has already been discussed. Okay, so here we cannot plot for all the values of W and B, that is minus infinity to plus infinity. Instead we are taking from minus 6 to 6. Okay, so we are finding the error for all values of W and beta between minus 6 to plus 6. In the guesswork we have taken only few values of W and beta, W and B. Now we are taking all values of W and B from minus 6 to plus 6. But here what is the problem? We are not taking for all values of W and beta, all ranges, which I mean is all ranges, that is minus infinity to plus infinity. Now this is what you get. Okay, this is B, this is W, which is plotted for minus 6 to plus 6. Okay, now we are getting a error surface that is just like a flying blanket. Okay, now so please remember here, the red color means, the dark red color means more errors. Okay, so light red color means somewhat less errors. Okay, light blue means even less errors. Dark blue means no errors or minimum errors. Is it okay? Let me repeat. So remember this. So it depends upon the colors of this flying blanket. Red means more errors. Dark red means even more errors. Light blue means good. Dark blue means even good, more good or better. Okay, like this you can get error surface. But so what is the problem with error surface? We are not checking for all ranges of W and B. We are going from minus 6 to plus 6. Okay, it is also feasible. Okay, but it is somewhat better than the guesswork because we are taking all values of W and B from minus 6 to plus 6. Okay, now so in our guess somewhere it might be somewhere here. Okay, in our guesswork we got a last point which is 1.78 to minus 2.27. So there the error is 0. No, it might be in the dark blue region where error is almost 0. It may be somewhere here. The point may be somewhere here. Okay, somewhere here. The data point which is leading to 0 error is somewhere here. Okay. Yeah. So geometrical interpretation of the guesswork. So till now we have done a guesswork now. So these are all the points that we have chosen in the guesswork. How many points? These points. I have indicated all the points in the error surface. Okay, you can see. So these are points and these are outputs. So sometimes you're getting 0 error, sometimes more error, something like that. And these are the sigmoid functions for those guess points, the points that we have used to guess the parameters. Okay, this is a geometrical interpretation of the guesswork. Okay, so as of now guesswork and this error surface is not at all a good idea. Okay, let us go with a principled way of finding or learning the weights from the given training data. Okay, why this doesn't work always? Why? Because we don't know for which values of W and B the error is minimum. Okay, suppose in this example I have taken minus 6 to plus 6, but suppose if you take more values of this W and B, maybe some point you may get even less error. For some other examples, are you getting what I'm saying? So in this case, we cannot take all possible ranges of W and beta that are minus to plus infinity. Okay, so we don't know at which values of this W and beta error is 0 or minimum. Okay, so in this example we could able to draw this, because one more reason is we have taken only 2 points. In the training data, only 2 points. If there are more points, it is very difficult to draw the error surface. Okay, if you take more points, okay, of data, that is xi and yi, it is very difficult to draw the error surface. And furthermore, you cannot draw this error surface for all ranges of parameters W and B. Okay, for these two reasons, it is also not feasible. Okay, so we need to go for a principled way of learning the weights. Okay, so let us see that in the next class. Stop here. Thank you.